Well, we've really been putting these polynomial problems through the ringer. You guys have learned all about the graphs of polynomials, their end behavior, and their behavior with turning and roots. And then we got into the fundamental theorem and found out that if we solve a polynomial, we can also connect that to a graph. And well, now we're ready to write a polynomial. We're ready to write a polynomial equation. Now, in math class, when you're writing an equation, we typically think that we're doing something backwards. The truth is that's what we're doing. We're going to end up as our final answer being the equation instead of starting with the equation. So the question becomes, how do we write an equation? How do we get a final answer that's an equation? Well, it depends on what you start with. It depends on if you're given the factors, or maybe you'll be given the roots. Or if we flip over to the back here, well, come on. If we flip over to the back, we'll be given a graph. So how are we going to write an equation given each of these? Well, you'll find out that it's just a little bit of a progression. You see, if you have the factors, isn't it true that the factors actually make the equation? Yes, it's true. The factors make the equation. If you multiply them together, yeah, that's all we got to do. We're going to multiply these factors together. And when you expand that all out, you're going to have an equation. We just got to multiply very carefully. Now, as you can see, I'm suggesting that we first multiply the binomials. That is, that we do a little FOIL method, right? If you do a little FOIL method, you're going to get x squared, 3x, minus 2x, and minus 6. So we multiply that all out, and we get x squared plus x minus 6. But there's this red x in front of all this, and that red x is now going to distribute or multiply to each of these. And so when I'm all done multiplying all this together, I'll get an x cubed, an x squared, and a minus 6x. But remember how we started. We started by multiplying the factors, basically by putting all the factors together. Does it work every time? Well, yeah, it pretty much works every time, but there might be some special events going on, like maybe a problem that has a multiplicity. Now, what we've got here is x minus 3 being a factor and x plus 4 being a factor, but x plus 4 has a multiplicity of 2. That means that I have 2 x plus 4s. That means I have 2 of those factors. Well, guess what? You want to multiply these together. You want to multiply together your factors. And notice I'm starting with the x plus 4, x plus 4. The reason I'm starting with that is because I'm pretty sure I know how to multiply those. In other words, you're going to kind of get a special result. You're going to get x squared. You're going to get plus 4x and another plus 4x, which is going to be 8x. And then you're going to get 16. So it's just a little easier to multiply those together first. Do you agree? Well, I still got some work to do. I still need to multiply everything on the left to everything on the right. And that means I'm going to do a triple distribute. Now that gives me x cubed, 8x squared, and 16x. But then I got to turn around and multiply negative 3 to all 3 of these. Again, kind of a triple distribute. Now that's going to give me a minus 3x squared, a minus 24x, and a minus 48. You can see that I kind of organize those answers vertically because when I add all of the like terms, that is when I add the x squareds, I'll get 5x squared. Well, I got x cubed, but also get 5x squared. And then we'll get, what, negative 8x and minus 48. So we did the same thing, but it took a little more work. We had to multiply everything together. You try. You try. You try to write a polynomial that has x plus 7, x plus 5, and x, which has a multiplicity of 3. Yep, are you trying? You want to try to set up your factors. You basically want to put together all the factors. Now, you're right if you're putting x plus 7 with x plus 5. So what's up with this x with a multiplicity of 3? Well, doesn't that just mean that I have x cubed? In other words, I have an x, an x, and an x? Yeah, that's all it means. I just have an x cubed, all 3 of those. Probably want to multiply these binomials first. And then all you got to do is distribute the x cubed. And when you distribute that x cubed, everything's just going to pump up by 3. So I have x to the 5th, now 12x to the 4th, and a 35x cubed. So if you're given factors, all you got to do is multiply all those factors. So what happens if you're given roots? What happens if you're given roots? Well, remember, roots are always connected to a factor. Roots are always connected to a factor. Wouldn't it be true that x plus 3/8 would have to be a factor? Or wouldn't it be true that x plus 4 would have to be a factor? Yes. Those roots are connected to those factors. Now, there's something a little goofy about this factor here, this x plus 3/8. We never work with factors that involve integers. That's because you always take that 3 and that 8 and you kind of rearrange them, reposition them so that they are written more like, more like the 8 actually being with the x, leaving the 3 to be my regular factor. So what do you think? Is negative 3/8 still going to be a root of this factor? Yes, but now the factor is written with integers. And again, all I really did was just kind of rearrange the 8 to go with the x, and then the 3's by itself, thereby creating 8x plus 3. And again, I still have my x plus 4. Well, just like any of these problems, you still want to write the equation. So keep in mind that now I got to multiply this all together. And when you multiply this all together, you're going to do some distributing. Can we kind of just talk about the 32x that you get out here and the 3x that you get right here? That's going to be 35x's. And so if you multiply this all together and expand it, you now have your equation. So roots, they actually go with a factor. Okay, now what are we going to do? We've got an imaginary root. We've got an imaginary root. Well, I'll tell you what, sometimes it's helpful to still record what we know is true, that x plus 2 is going to be the factor that goes with negative 2. But we still got to figure out what to do with this 3i. Now, one thing you want to realize is that 3i actually has a partner. Remember, 3i will always come with a pair. That means negative 3i has to also be a root. Now, I don't know if that's helpful or not, but it's supposed to help you kind of realize that any imaginary root will always come from an x squared. You see, that x squared is what's going to produce both of these answers, mainly the plus and the minus. So now, what number produces a 3i? What number produces a 3i? Is it 3? No, it's the number that 3 came from. It's a 9. And all we have to do now is realize that it's always going to be a plus sign. Why is it always going to be a plus sign? Well, because I want to subtract this 9 and get a negative 9, right? So you kind of have to work backwards. Imaginary numbers, they always come in plus or minus pairs. They always come in plus or minus pairs. And now we have that's why we had x squared, and then of course the plus 9. Now kids, you still want to multiply these together, and when you multiply them together, you get x cubed, you get 2x squared, you get 9x, and you get 18. So we get x cubed, 2x squared, 9x, and 18. What about this next problem? Do you guys think you can find the roots for can you find the equation that goes with these roots? You want to start by trying to write the factors. See if you can write the factors. What we're doing is picking out one of the roots that has an easier factor, you know, like x plus 3, definitely has to go with negative 3. How about these zeros? Do you realize that each of those would be associated with just the letter x? So basically I have an x and an x, or if you would like to write that as x squared. If you would like to write that as x squared, that would be fine. So what about the square root of 2? You got to kind of think, where did that come from? Now, it definitely came from an x squared. That's the only way we're going to get that square root. So what number did we square root? What number did we square root? That's right, it's a 2. Now this time I want a minus sign because I don't want an imaginary number. So I'm going to use a minus sign, so I end up with the square root of positive 2. What are you saying? You're saying that this should also be negative root 2? Yes, there should be a negative root 2 that also goes with positive root 2. You see, that's because irrational roots, now irrational roots are roots that have a square root. They also come in plus or minus pairs. And so we will always have an x squared. We will always have an x squared when we see a square root. Let's clean this up a little bit. Basically, I'm going to get ready to distribute. I would say that you're welcome to just start working left to right. I don't know if it's any easier or harder to just kind of jump in here and start to distribute. But you do want to realize that you're going to have to keep going. You're going to have to FOIL and expand all of this. Now, x cubed and x squared is x to the 5th, and then minus 2x cubed. And then I think I'm going to multiply here, that is distribute 3x squared to x squared and get 3x to the 4th. And then one more time, distribute, and you get minus 6x squared. Now normally you want to write your answer in what we call standard form. Standard form would mean that it's in order. So I am going to kind of recopy a little bit here, but basically I'm going to put my 3x to the 4th, then my minus 2x cubed with the other terms bookending that. What kind of graph do we expect? Oh, that's a good question. What kind of graph do we expect? Well, one thing that you want to realize is that we can know a lot about the graph just by the original problem, just by the original roots, right? Those roots are actually most of what we need for the graph. So I should, with 100% certainty, be able to mark negative 3. I should, with certainty, be able to mark 0. What about those root 2's? Well, those root 2's are in here also. One of them's positive root 2 and one of them's negative root 2. So I've got four roots marked, but yeah, there was some multiplicity business going on with some of these also, right? Yeah, because we actually have an answer to the 5th power, we know that we actually need to make sure our behavior is opposite. And of course, going up, not that way, but going up to the right so that it ends up going down to the left. So what do you think? Pass through this point, touch this point, right? Touch at 0, pass through negative root 2, and then come on back through negative 3. If you want to, you could check that graph using Desmos, and you would see that our graph matches very well. So if you're given the roots, a little bit trickier. If you're given the roots, you have to kind of think backwards. You have to think backwards about what would be the factors. And sometimes your factors are going to involve an x squared. Keep in mind that you're always going to get an x squared if you have imaginary, or you're always going to get an x squared if you end up with an irrational. And an irrational is something that have like a square root. One more scenario. If you're given a graph, do you see what's going to happen here? We really just have to add one more step. We have to kind of work backwards through what it is that we know. And you're exactly right. We want to start with the roots. Those x-intercepts, they are definitely key to this equation. Now, if we do a little careful counting, you have negative 6, negative 1, and 6. So those would be my roots. Again, negative 6, negative 1, and 6. And of course, if those are the roots, then I'm going to have factors. Okay, remember, each root has a factor, and I can be 100% sure that the factors will match with each of those roots. Now, two of my factors kind of go together. Wouldn't it make sense for x plus 6 and x minus 6 to kind of be multiplied together first? I think that that's a good idea. So I'm going to multiply the x plus 6, x minus 6, and that's going to very nicely turn into x squared minus 36. And I still have my x plus 1 that I have to continue to multiply. So we're going to distribute x squared, right? X squared onto each of those gives me x cubed and x squared. And then minus 36 onto both of those is minus 36x and minus 36. Seems pretty straightforward, but is there anything else? What else could there be? What else could there be? Yes, the end behavior. The end behavior. This graph, even though it's passing through these roots, it's going down to the right. How do you make an equation go down to the right? You need to have a negative out front. Now watch, kids. I'm going to put a negative out front, but I have to multiply everything by a negative. You have to multiply everything by a negative. Now, when you multiply everything by a negative, you actually end up changing all the signs, but don't worry, it doesn't change the roots. The roots are still going to match. I'm talking about these x-intercepts that we started with. So each of those matches. But look, there's a way that we can kind of check our answer. That is, we can use the y-intercept. And we can see that there's a positive y-intercept, which matches pretty nicely with the one that we see in this graph. If you really wanted to, you could check this answer on Desmos. But you'll find out that it is right. Yep, I'm kind of waiting and wondering, do you want to try to do this on your own? Do you want to try to do this on your own? You should be starting with the roots. Those are the x-intercepts. Now, as you list those roots, you very well should and might notice that one of them has a special behavior. It's just touching. It's just touching. That's right, it's going to be repeated. Now what we're going to do is just assume that it's only repeated once, or excuse me, yeah, it's counted twice, so it has a multiplicity of 2. We're not going to go with a higher multiplicity. We're not going to think that it's maybe 4 or 6 or 8. We're just going to stick with the first even multiplicity. Are you writing the factors that go with each of these? X minus 3. Not x plus 3, but x minus 3. X plus 4 and x plus 4. Kind of look like a problem that we did on the front of the paper. Yeah, it probably would make sense to multiply those x plus 4s. You might as well multiply them first. So we get x squared, 8x, and 16. And then we get x minus 3 that's going to have to multiply in. Yeah, you have to kind of see that this is going to be like one of those triple distributes. You got to kind of keep it organized, but basically you're going to distribute x onto all of these. Let's do it. That raises it up to x cubed, 8x squared, and 16x. And then you're going to distribute negative 3 onto all these. So that gives us negative 3x squared, negative 24x, and negative 48. I kind of feel like I've seen these numbers before. Are they the same as on the front? Well, we get x cubed, add up these x squareds, and that gives you 5 x squareds. Negative 8x and negative 48. Is there anything else? I don't think so. If you look at the end behavior, you would conclude that it is going up to the right, and we already have a positive leading coefficient, so we don't need to change anything. And if you look at the y-intercept, negative 48, you can see that it's negative, so that's a good match. I think we got it. Again, x cubed, 5x squared minus 8x minus 48. So if you're given the graph, you gotta start with the roots and then work your way through the factors to the equation, but be careful about the end behavior. Make sure that that matches. What's this? Just kind of a little exit question. A polynomial of third degree can have 2 and 2i as zeros. Third degree. Third degree means that this thing's going to be x to the third. But third degree also means that you're going to have 3 answers. How come I only see 2 answers here? Oh, wait, you're right. There are 3 answers. This imaginary answer actually represents, and well, I should say guarantees, plus n minus 2i. So I've got 1 answer, 2 answers, 3 answers. It looks like that this definitely can be and would be true. I can have a third degree, an x cubed, that would have these numbers as zeros. Now, the practice problems that goes with this set of notes is actually a little bit of a graded activity. It's the polynomial equation cards. So you're ready to do the cards. You can either grab them online digitally, or I'll have them for you to handle in the classroom.